So we're continuing on methods of the method of partial fractions, and this time the example is 1 over x times 1 plus x squared. That's the integrand that we're trying to attempt. So the question is, have we done step 1? And step 1 is done. 1, the degree of numerator is 0, degree of denominator is 3. So 1 is done. Step 2, is the denominator factored into linear times quadratic that cannot be factored into real. Does not have real solutions, basically. And so x is linear. X is the linear polynomial with solution 0. And then we have 1 plus x squared. And remember, 1 plus x squared cannot be factored. The solution to this is x equal to I or x equal to negative I. So this one does not have any real solutions neither. Therefore, the denominator already in that factored form. It turns out that a lot of times when you're doing and a lot of times in differential equations, when you're using partial fraction methods or you're using it in circuits, you already have the denominator factored in the right way. Now, that's the nice part of it, basically. And so now, step 3 is that step that we have to put this this fraction or quotient into a nice format. So for every linear, you want to have a constant numerator, and there is only one quadratic, and so I put the quadratic down like that. And for quadratics, you want to have basically a linear numerator. So I'm going to put in bx plus c. And now from then, do the usual. Basically, I want to set this fraction equal to these partial fractions. So what do? I add the partial fractions, and then I solve for a, b, c, d. Here to c, not d. And so it would be a times x squared plus 1 plus x times bx plus c divided by x times x squared plus 1, right? And so that would be a x squared plus 1 plus a distributes plus bx squared plus cx, right? And then over x times x squared plus 1. Now, this is supposed to be equal to the fraction or the quotient function, and therefore denominators are the same, so I have to set the numerators the same. And in this case, I'm going to end up with 1 is equal to a x squared, let's say, plus bx squared plus cx and plus a. And you notice that I put the x squared together because what is going to happen is that I want to put make the coefficient of x squared equal to the coefficient of x squared on the left side, and I want to make the coefficient of the x equal to the coefficient of x on the left side, and so on and so forth. Here, the easiest one to solve is a. A is the constant on the left side is 1, so a is equal to 1. And the next one is, I guess, c and a were the same, right? And c times x, there is no x on this side, so the coefficient of x on the left side is 0, so c is equal to 0. And then I have a plus b coefficient of x squared is 0 on the left side, so b is equal to negative a, or is equal to negative 1. Now rewrite the entire thing, and what you get, I actually am going to write, no, it's okay. So x over x squared plus 1 is really equal to, go back here, a is 1 over x plus negative, that's right, negative 1 times x, which is negative x over x squared plus 1. C was 0, right? Now take the antiderivative of that. That's the next step. And so the antiderivative of this is going to be antiderivative of the first term minus antiderivative of the second term. In this case, the antiderivative of the second term is going to be basically you're going to use a u substitution. This one is obvious. That's just natural log of absolute value of x. And u substitution is that. And du is 2x dx. And so the entire thing is, for the first one, is natural log of absolute value of x minus natural log of x squared plus 1 divided by 1/2 plus c. X squared plus 1 being u. So that said, now we do another, basically another one involving the quadratic with no real solution.